Hey everyone, welcome back to the Altium tutorial series. I'm Chris, and I am going to do tutorial 4 today. And so what I've done ahead of time is we have defined a PCB here, and we use the mechanical one layer to do that. So these are, you can see these are actually like lines and arcs, and we use the design board shape from selected objects. We talked about that in the last tutorial a little bit. And I've also gone ahead and made a schematic. It's a very simple one from a different project that I was using that I think illustrates the points well. So just like before, I'm going to come to Design, Import Changes. I want everything except this room. I'll execute them. And here we go, we've got all our parts. So I'm going to hit G, set my snap to 100 mil, and I'm going to start very roughly organizing this big list of parts. So I can multi-select them, and I can drag them over here, and I can start thinking about what makes sense for this PCB. So a couple things you want to consider. The first thing is I have data input and I have some sort of output. And in this case, my input is going to be the switches that the user is going to press. So I want those to be on the left of my PCB. I think that will look nice and make the most sense. And then I also have some LEDs that indicate the output state. So for example, I have LED 1 here. LED 2 here, so I can place those out. I think I'm going to put Q1 here and Q2 here. I have a reference I'm looking at because I want this to be pretty close to the last time we did it for the previous tutorial, so that it lines up with tutorial 5, of course. But overall, yeah. So why am I doing it this way? So the reason I'm doing it this way is because I have these connection lines, which we've talked about before, and I'm trying to untangle them. So there's a couple of things you want to consider. First of all, these ground connections, we're actually going to use a different method of connecting all of those. Once we're done routing every other trace, we're going to fill in all the dead space on this PCB with copper that connects to these ground planes. So we don't actually have to route them, which means we don't actually have to consider them very much when we're laying out our parts. And a quick trick for this is to go to View, Connections, and then we can say Hide Net. And if I click right here on this ground net, whoops, I click right here. Why is it doing that? Let me zoom in a little bit. If I click net name. That's what I wanted to do. Anyways, now that the ground is hidden, I don't have to worry about these connections when I go to untangle these wires as I place components, and that makes my life a little easier. By the way, you can see that when I hit the space bar, I'm rotating in 45-degree increments. That's because I went up here to my preferences, I went to general, and then right here I have my rotation step set to 45 degrees. So that's something you might consider doing to make your life a little easier. So, like I said, I'm untangling these nets. I'm putting things where they kind of make sense going. I have my power input. I think that makes sense to kind of put that at the bottom. I'm honing in on these like key areas. So for example, the power, the data input, the output. Whoops, didn't mean to do that. I just want to change this designator real quick. And I'm using those to kind of inform the general flow of the board. Right, so it makes sense to have this kind of on its own, close to an edge, so it's easy to give power to the board. It makes sense to have these both be on the same side so that it's not confusing to a user. These are things you want to consider when you're designing your board, which is most likely a lot more complicated than this. If I rotate that, I think it makes sense. This is a capacitor, and so here's a good example of something you got to be careful about. So there's a lot of 5-volt things, because a lot of things connect to power on this board. So it's going to look like it makes sense to put it, somewhere over here. And the truth is that it doesn't, because this capacitor is just there to filter the input power. So I want to make sure that this is actually close to the input. And there's going to be a couple cases, things like pull-down resistors and stuff like that. You want to put it close to, if it's a pull-up resistor, you want to put it close to the pin that it's supposed to be pulling up. Filter capacitors, just like I'm doing here. These are just things to think about. One thing I just noticed is that I'm having trouble selecting this, and the reason for that, whenever you're having trouble selecting things, turn your attention up to this funnel icon and make sure that you actually have those things available to you. For example, right now, the only thing I can select are components, because that's the only thing that's highlighted here. So I can only click on components, I can't click on designators. So let me toggle that. Now I can click on anything, including text, and now I can select and move this. Sometimes when you're having issues clicking on things, that's the solution. So I think it's a good thing to point out. So I'm going to continue on, putting my parts roughly where they belong. I think I'll put this one goes here. You can see so I'm trying to shorten these the best I can. And so let me talk about some other considerations. So you want to think about, where your sensitive signals are. For example, if I have some, very important communication line, I would make sure that I don't force myself to have to route it next to very noisy or very high current lines. I wouldn't want to put, sensitive lines near things that are driving motors or something like that. That wouldn't make a lot of sense because I could get some interference going on between those traces. These are kind of considerations that matter more for more complex and professional boards, and I think a lot of SDP projects might not have to worry about factors like that. But it's something to think about. We're trying to design, functional, semi-professional looking boards here, right? So these are just things to consider, and we want to use the best practices anyways. So yeah, I think this is starting to look pretty good. So I'm going to introduce you to a couple tools that I think will be helpful. Let's say that I just put this, here, for example. Realistically, I might want my output to be in line with my input because I like the way that it looks. I want things nice and square. So if I multi-select these, press the A button, I get my align menu, and I can say align vertical centers. So now I have a crosshair, and I'm going to select this part as my, I'm going to say that the placement of this current part is correct, and move the other one so that it matches it. And that's exactly what it just did. It just moved this part up, so now it's perfectly in line with that part. I should do that again here just to make sure it's right. Align vertical centers, just like that. Yeah, moved it down a little bit. And also, at the same time, I want to align these. So I align horizontal centers. And just like that, now these things form like a rectangular placement pattern, which looks nice and professional. So let's keep going with this. Can I do some things here? I think I can rotate this. Yep, and so that kind of untangles these nets. I think I can do the same thing down here. Yep, I think that's a little better. I have a cross there, but we'll deal with that. I'll talk about in the next tutorial how to deal with that. And I think overall the general shape of this is coming together. So there's a lot of things to consider. You want to keep components that support other components. For example, if you have an IC that requires some passive components, resistors and capacitors, for it to function, you want to keep those very close to each other. You always want to shorten your traces as best you can, and you want them to be as untangled as possible so that there's not a ton of crossing going on. There's a lot of things. I would recommend you do some research online, especially you can look up, for the board you're designing. Certain boards will have certain considerations. High frequency boards come with their own set of considerations. High current boards have some things that you need to consider. You can to consider like heat dissipation in the board, and that all influences how you lay the board out. So these are just things to be thinking about. This board is a very simple, discrete, bistable multivibrator. All of the components are through-hole components, so the design demands are not very strict in this case, and that's why I'm not worrying too much. I definitely should rotate this. That makes a big difference. And I think for now this is good enough. So this is a pretty decently organized board. I'm trying to make it symmetrical. I think that'll look nice when I go to design it. It'll make it easier to route, most importantly. I think I'm going to move these back a little bit and maybe move these forwards a bit. And you'll see in the next tutorial how I route this. So I want to call your attention to something right now, and that is this particular silkscreen right here, the yellow. You can see that there's these green circles on it, and those are error markings. So that means that I've got an issue right now. And you might be wondering, how does it know that there's an issue? Like, clearly you can see that the issue is that the gap right here is too small. It's less than 10 mil, but who said it needed to be 10 mil in the first place? And that's where your rules come in. So you go to design, and you have rules, ... I can open that, I get a dialog box, and this is the rules panel. So this is a really helpful thing, and after you do your very rough layout and placement for your components, you want to come right here and define some rules. So I expand this electrical category. I can see there's a bunch of categories again, like subcategories, And so let's look at clearance. So what do I have? This here is a description of the clearance rules that the PCB editor is going to refer to when deciding if there's errors or not. And I can do some things with this. So let's open up a file explorer. Let me go to JLC PCB, and I will put this up on the screen. Okay, so why am I here? So every manufacturer that you might consider, I'm just using JLC for example, but you could use Osh Park or someone else. They're going to have this capability section. Maybe it'll be called services or something different, but the bottom line is that they're going to have information about what they are capable of manufacturing. And it can't just be anything. For example, if I go here, I look at drill hole size. You can see they have a capability section, 0.2 millimeters to 6.3 millimeters. And what this means is that if I try and send them a file that has holes outside of that range, they're not going to manufacture it. They will either skip over that element entirely and not include it in the design. They will reject the file. They will get as close as they can, just do their best, and you don't know what you're going to get back. So in general, you want to consider these capabilities when you're designing. So let's take a look at their clearance section. I'm going to scroll down a little bit. I'm not going to have it on the screen because I want to show Altium right now. Maybe I'll just show it for a moment here. So you can see here's their minimum clearance section. So hole-to-hole clearance, via-to-via clearance, pad-to-pad clearance, etc. So let's take a look at this one. Pad-to-pad clearance. Pad without hole, different nets. 0.127 millimeters. So if I come down here, I go to SMD pad to SMD pad, where these, this row and column intersect, and I have 10 mil. And it's only mil right now because back in my PCB editor, I'm using mil. You can see the bottom left here. I have my all my measurements set to mil. If I hit Q, that'll flip to millimeter. And then if I were to open that window again, everything would be measured in millimeters, which might make more sense for this. In the end, it doesn't matter because in Altium, you can just type 10 MIL. And if I hit enter, it'll actually switch to millimeters or whatever the default unit is. So according to JLC PCB, the minimum pad-to-pad clearance is actually 0.127 millimeters. And so I can change that. And that's going to affect my routing and my part placement in here. So I can actually now move things closer together without getting an error. And that's good. And it takes a long time to do this, but it is worth your time because you're going to ensure that the PCB you end up with is going to be correct. Most of these are actually right for JLC. There's only a few that you're going to want to change. So let me scroll through and try and find a couple. Let me scroll down a bit. Really important one is right here, minimum trace and width spacing. So if I go back to my rules, let's leave clearance for now. Let's go somewhere else. If we go to routing, width, and then actually find this width rule, you can see the minimum width, the preferred width, and the maximum width for my traces. And according to JLC, doesn't look like they have a minimum, but they do have, it doesn't look like they have a maximum, but they do have a minimum. And the minimum spacing between traces is 5 mil, that's good to know. And the minimum trace width is also 5 mil. So let's put those things into Altium. So the minimum is going to be 5 mil. And that'll be for the top and the bottom. Whoops, 5 mil. And the maximum is going to be, well, they don't have a maximum. In our board, I think a reasonable maximum is maybe, 30 mil. That's a very thick trace. And what you should really be doing is going online, assuming you're using probably 1 ounce copper, unless you have a very special PCB that needs a different weight for your copper. You can calculate based on the current that you're carrying what these need to be. So for example, if I know that my board is going to consume 2 amps through the power trace, I can use an online calculator to find out what that thickness is going to be. This board right now is not going to consume a lot of power. It's a pretty low power board, so I happen to know that anywhere between probably 15 and 30 mil is going to be fine for what I'm doing. But I do urge groups for their project to actually go and use a calculator online or talk to some M5 staff and make sure that their thicknesses are correct. So I'm going to say my preferred width, let's say it's, maybe it's 20 mil preferred thickness. So that's basically the default, and it needs to be between the minimum and the maximum. So there's one more thing I can do. I can actually come in here. If I right click on width, I can say new rule. Now I have width underscore 1, and I can create a customized rule, and this is really great. So if I go to, let's say I name this power width. So what I can do is create a specific targeted rule. I can say where the object matches nets that are part of the +5 volt category, I can apply a different rule to only those nets. So what I'm basically saying right now is this is the default rule. All traces need to fall between 5 and 30 mil with a preferred width of 20. But if you fall into the power trace category, then the minimum should be 20 mil, not millimeters. 20 mil. The maximum should be probably, I don't know, let's say 40. We're not going to use 40 for our actual routing. And the preferred, let's say it's 25. So it's a little thicker than all the other traces by default. So what we have here is a rule that is going to target all the power traces and make them thicker than the data traces, or any other trace for that matter. And all I need to do is make sure, if I click on width right here, that this power width has a higher priority than the general width. And what that means is that basically when Altium goes to do this error checking, it's going to look at a certain trace, then it's going to start with priority number 1 and say, does this trace fall into this scope? If not, it'll skip it, and if it does, it'll just apply the rule. What that means is if I had this width rule higher than the power width, when it came to a power trace, it would say, does this power trace fall within the scope of all? Obviously it does, and then it would apply the width rule, which we don't want. So we want to put our more specific rules at the top and our more general rules at the bottom. And then you can click apply, and that'll happen. So there's a lot of these. You should go through and look at them. You can use the JLC website as a rough guide of what you should be saying for most of these things. A couple I want to look at, solder mask expansion, is going to come up later. You'll see numbers for that on the JLC website or whatever manufacturer you use. I want to look at manufacturing. So this is going to be, this error right here is actually a silk to silk clearance, i.e. a silkscreen to silkscreen clearance error. So right now we're requiring that there is 0.254 millimeters of space between silkscreen elements. And that's actually not a bad number. JLC or your preferred manufacturer will give you a better number. So there are other ways to resolve this error that we're going to look at, but now you know at least where that is. I think a relatively important one that's going to come up later in this tutorial, in later tutorials, is the Polygon connect rule. So when we go to fill in all the dead space on the board with copper that connects to the ground plane, we also need to connect that dead copper to the ground pads of our components. So this is going to be how it does that. And because there may be some significant amount of current going through those, you can specify a width. So let's say our conductor width is going to be 30 mil. Rotation 90, I can set it 45 degrees, that looks kind of cool, but let's leave it at 90. Let's use 4 conductors, and let's have this air gap. And the reason we have this air gap is because it actually makes things a little easier to solder to. It's a thermal relief when we go to solder to this pad, so that we're not heating up the entire ground plane, we're just heating up pretty much only this pad. And I'll say apply, and that's good for now. So we definitely recommend that you go through and look at a lot of these. You will not need all of them. For example, some of these I haven't touched, unmodified Polygon. Some of these I'm not even sure what they exactly do. I'll quickly go through and tell you some of the most important ones are clearance rules. You should review your short circuit rule. Your width is very important. Your via style is very important. For example, this is the annular ring. That's the ring of copper around a hole. So you want to make sure that that is correct to the manufacturer standards. Definitely look at your solder mask expansion, your Polygon connect, look at most of your manufacturing rules, and feel free to ask M5 staff to help you through this. This is a little bit intimidating the first time you do it, but as you do it, you'll become comfortable with okay, what's important. Obviously, a lot of these apply to some, Altium is equipped to handle some pretty crazy board designs, boards that operate with gigahertz frequency lines, or like huge currents and stuff like that. So there are a lot of rules here that are specific to targeting those applications that are not going to come up for almost any STP project. So once you have those set, you can confidently route the rest of your board, and you'll end up with something that you can be pretty sure is going to work. Theoretically, if you define your rules perfectly and you observe them for your entire design, you should end up with a product that it should work basically on the first try. Is that actually going to happen? Probably not. It's pretty common to have to redesign a board. Hopefully it works on the first try. I mean, it's definitely not impossible, but it's definitely not a promise, even if you are very careful with your design rule check. All I can tell you is that the more careful you are, the better chance you have of getting it right. So I'm going to move this, and you can see I just cleared up that error just by moving that a little bit to the side. So now I don't have that error. By the way, if there are errors in your board that you know about and want to ignore for the time being, for example, let's say I have this here, there's an error, and I know I'm going to clear it up later. There's just a couple things I need to do first. Tools, reset error markers. I'll get rid of those for now, but if I ever go to move this later, they'll come back, right? So it's like a temporary way to just disable those very annoying green dots, which might be distracting you while you're trying to get something else done. So in the next tutorial, we're going to route this. We're going to see some routing practices, and we're going to move on and hopefully come to a state where we can actually order this PCB. So there's definitely a lot more placement things to be done. You should take a lot more time to do this, of course. I'm just trying to generate a quick tutorial to get you guys started. Obviously, when you're doing your STP project, which you're going to be graded on and everything, you want to take your time and do a really good job. So like I said, feel free to ask us questions if you have any, and thanks. See you in the next tutorial.